Hello students, in this video we'll compute the Gaussian curvature of a torus. Let's consider the torus. Torus is parameterized as follows. It's parameterized by r of theta and phi. I'm going to put into arclength parameter in terms of my rotation curve over here. So there's going to be an a plus b cosine of theta over b, and then times the cosine of phi. Then we have an a plus b sine, cosine also, not sine. That's going to be a cosine. I'm rotating that whole circle. Cosine of theta over b times the sine of phi. And then a b sine of theta over b, like this, okay? That's how I parameterize my torus as a surface of revolution. And so I want to compute, and the reason I'm doing this is I want the first fundamental form to be in a nice compact form, okay? And so now let's compute the first fundamental form. So what's my r theta going to be? So my r theta over here is going to be what? Is going to be just the derivative of this thing over here. So there's no thetas over there. So if I do a theta derivative of this thing, I'm going to have the b's are going to cancel out with negative sine theta b. So it's going to be negative sine theta over b cosine phi, comma, what? The theta derivative of this thing is going to be the same thing over here, negative sine of theta over b times the sine of phi. And then finally the derivative of this is going to be the cosine of theta over b, cosine of theta over b. Good. My r phi going to be, my r phi over here is going to be what? Is going to be, let's see what we're going to have. The phi derivative of this thing over here is going to be this expression over here. So it's going to be a plus b cosine of theta over b, like that. Same thing over here with a sign now and a negative sign. So I put a negative over here and then I put a sign over here for the phi derivative. Phi derivative. And then we'll have the same thing over here for the first entry over here. The first entry is going to be a, now it's going to be a positive. So it's going to be a plus b cosine of theta over b. And now it's the cosine of phi, and then finally 0, right? So we can easily check that if I do a dot product of these two expressions over here, the r theta and the r phi, it's trivial to check that r theta dot r phi is going to be equal to 0. That's easy, right? What's r theta dot r theta? That's why I have the over b's everywhere. If I do this and this, what we're going to have a sine squared of theta over b, sine squared of theta over b, cosine squared phi, sine squared of phi. Those are going to add to 1. So it's going to be a sine squared of theta over b, cosine squared of theta over b. So it should be 1 over here. Beautiful. That's going to help me find my Gaussian curvature really in an elementary fashion. What's my phi phi? R phi dot r phi is going to be what? We'll have this expression squared, sine squared, cosine squared, so we just get this expression over here. So which is going to be a plus b cosine of theta over b, like that. And it's going to be quantity squared, right? So this squared plus this squared. So this squared. Beautiful. All right, so therefore my first fundamental form, so the first fundamental form is going to look like this. Is going to look like, so 1, first fundamental form, is just going to be a d theta squared over here, plus what? Plus, I'm going to have a plus b cosine of theta over b, quantity squared, d phi squared, right? And I know my first fundamental form is in this structure, so this has exactly the form of what? The form of d theta squared plus g of theta and phi squared, d phi squared, right? We have a formula for the Gaussian curvature. We know that if the matrix form in the Gaussian curvature K, take that equal to 1 over g, so this would be 1 over g of theta and phi, times the second theta derivative, of this thing, with a negative sign, of course. Second theta derivative of what? Of the g function, g of theta and phi. So let's do it. It's going to be negative 1 over what? Negative 1 over the square root of this thing, which is going to be a plus b cosine of theta over b, like that. Excellent. And then I got to do the second theta derivative of this thing. So it's going to be the theta derivative. I'm going to do one theta derivative of this expression over here. So if I did a theta derivative of this expression over here, what would it be? It would be a negative sign of theta over b, like that. Okay, that's the derivative of the square root of that thing. And therefore, this is going to be what? The derivative of sine is going to be cosine, right? So this is going to be a positive. So I'm going to have a positive cosine of theta over b. Over, I get a factor of b in the denominator, over b, and then a plus b cosine of theta over b, like that. Excellent. Okay, and so that's the Gaussian curvature. That's beautiful. Now let's find the principal curvatures, right? So to do that, I'm going to compute the normal vector of these things. So let's compute the unit normal vector. So how am I going to do that? So my n vector is going to be r theta cross r phi. So what we're going to do that. So we're going to get nothing over here. And then the off terms over here, we're going to have this expression. So I'm going to call this coefficient expression over here, I'm going to call that capital D, right? So this is going to be capital D. And then we'll have a cosine phi, cosine phi, and then a cosine of theta over b, right? And that was the off diagonal entry, right? So that term gets a negative sign, right? So that's a negative of this for negative of that. Good. And then if we do the j entry, what are we going to get? If we do the j entry over here, we're going to cross out the middle term. So this term is going to be hit with nothing over here if we do the j entry. Then I'm going to have this term over here and this term over here. So that's a negative for j, a negative, and a negative. So I have three negatives over here. That's going to be a total of negative. So I have a negative d. Then the sine of phi, the cosine of theta over b. Sine of phi, the cosine of theta over b. Like that. Great. And then what? And then we're going to have the final term over here is going to be what? So we're going to have d cosine squared phi, and then with a negative, and then with a negative, 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 we're going to have a d sine squared phi sine of theta over b, right? So that term is going to give me a what? That term is going to give me a b with a negative, of course, right? Because it's the negative up here, right? And then negative, 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 we're going to have a negative d, like so. And then we'll have a cosine, and we'll have a sine of theta over b, right? Sine of theta over b. Beautiful. And then what's the length of this vector over here? Well, this thing squared plus this thing squared plus this thing squared, I'll have a cosine squared sine squared. So this is going to be a d squared cosine squared b, d squared sine squared b, right? So that's going to be a d squared. So in other words, I can just cancel out the d everywhere, and that will give me a unit vector, right? It's my hat. And hat is just going to be negative cosine phi cosine of theta over b. Then negative sine phi. It's a negative sine phi, good. Phi cosine of theta over b. And then finally a negative sine of theta over b is my normal vector, the surface unit normal vector of the surface. Great. Let's give you the second derivative so I can view what the second fundamental form is going to be, right? So my second fundamental form over here is going to be what? So my second fundamental form, so what's my r theta theta going to be? My r theta theta is going to be what? Is going to be a 1 over b, negative 1 over b cosine theta over b cosine phi, and then I'm going to have a negative 1 over b cosine phi, be negative 1 cosine theta over b, and then a sine phi, and then a negative 1 over b, and then a sine of theta over b, like that. Great. It's my r theta theta. It's my r theta phi. Is going to be what? Is going to be negative sine theta over b, negative sine theta over b. And then a, so I have to do the phi derivative of this thing, so it's going to turn into a plus sine phi. Over here, we're going to have a negative sine theta over b. And then a cosine phi. And then finally a what? And there's no phi over here, so that's going to be a 0. And then with the phi derivative, the phi derivative is going to be what? The phi derivative is going to be a total of what? The phi is over here, right? So that's going to be a negative d. And then that's going to be the derivative, that's going to be a cosine phi. And then over here we'll have a negative d sine phi, with a d sine phi, and then a 0. Okay, so we'll find the second fundamental form. So listen, the second fundamental form is going to be My second fundamental form, 2, is going to be, well, it's going to be r theta theta over here, dot with a unit normal vector right over here, right? Think right above it. Let's look over here what we're going to get. We're going to get cosine squared of phi, cosine squared of theta over b, a 1 over b, sine squared of phi, cosine squared of theta over b, right? So if I add those squares of those things, if I add those things squared together, I'm going to get a what? I'll get a sine squared 1 over b plus cosine squared phi 1 over b, right? So that's going to be a 1 over b times this expression over here. Then I'm going to have a positive 1 over b sine squared of phi. So that's just getting 1 over b, right? So it's going to end up 1 over b d theta squared. Beautiful. If I do r what? If I do r theta phi dot what? R theta phi dot this thing over here, then we have equal and opposites of exactly these expressions. So no mixed term over here. So it will be 0 d theta d phi. And then what's the last term going to be over here plus the last term? And the what? And the r phi phi dot this expression over here. And you're going to have a cosine squared phi with a positive sign with a d. And then I have a sine squared phi positive d. That's going to be d, expression d. And then the d, and then cosine of theta over b. Like that. Okay, excellent. All right, and so now what I can do is I can look at these things over here. So what can I say? I can look at this 1 inverse. 2 is my Weingarten matrix, right? And so this Weingarten matrix is going to be what? Well, it's going to be the inverse of what? The inverse matrix. So this fundamental inverse of this thing is just going to be what? The inverse is just going to be a 1, and then a what? A 1, because 0, 0. And then what are we going to have over here? Then we're going to have the inverse of this thing. So this thing looks like what? This thing looked like, this was like my factor d, right? So I'm calling this is the same thing as d squared over here, right? So I had to put a d to the negative 1 over here. So d to the negative 1. So that's going to be a d to the negative 2, right? That's the inverse of the first fundamental form, right? And the second fundamental form is given by this expression over here. So this is going to be a 1 over b, 0, 0, and then what? 0, 0, and then a cosine of theta times d. D cosine of theta over b. And what that tells me is that gives me my principal curvatures, right? My first principal curvature over here is going to be the eigenvalue of this matrix. So my first principal curvature K1 is just going to be 1 over b. Beautiful. And my second principal curvature K2 is going to be what? It's going to be a 1 over d times the cosine of theta over b. So it's going to be cosine of theta over b over this expression over here, over a plus b cosine of theta over b. And I know that makes sense too, because I know that this is my Gaussian curvature, and the Gaussian curvature is indeed a product of these principal curvatures over here. So for the torus, we've just found the Gaussian curvature. Now, of course, as theta is changing, the cosine can be positive or negative. So there's regions where there's positive Gaussian curvature, regions of negative Gaussian curvature. And you can see this over here too from like the changing of the sign. So there's points on this torus that are elliptic points, and there are points that are hyperbolic points over here by looking at this and setting K2 to be positive. K2 can be positive, K2 can be negative, and K2 can be 0 for certain points over here. So you can find different points on the torus where you have points of elliptic geometry and points of hyperbolic geometry. Thank you very much.